So the process we used to calculate the area under curve for velocity curve can be generalized in what we call a Riemann sum. So whenever we divide a domain of a function like this, or even an interval, right, in the domain of the function in irregular intervals, we call this a regular partition. So it's important that we name the grid points of that partition, those being the endpoints of each subinterval. We label them x0, x1, x2, x3, so on, up to an xn, right? So there's n plus 1 points from x0 to xn that determine n intervals, right? And each interval is going to be the base of a rectangle that we will use to approximate the area. Inside of each rectangle, inside of each subinterval, we choose any point, and that will be like x1 star, x2 star, whatever, that we will use to find f of that point as an approximation, right, for the height of the rectangle. So each rectangle will have area, base, right? Base is delta x, which is the size of each subinterval, right? So b minus a over n, so the whole thing divided by how many subintervals we have, times the height, and I chose f of xk star, whichever xk star I decide inside of the subinterval, to be the height. So that here, right, if I want to zoom in just to be clearer, this is x1 star, and this is f of x1 star. So this is the height of the first rectangle, and this is the base, which is the same for all of them, right? So the area of the first one is f of x1 star times delta x. The second one has the same base, and the height I chose f x2 star, so that will be f of x2 star will be the height. So when I add all of this, that will be a Riemann sum, right? So the Riemann sum is this sum here of the areas of all rectangles, each having the base delta x, which is the same for all of them, and each having the height f of x1 star, f of x2 star, and so on, being a point chosen within each subinterval. You can choose any one, but in 3 of the cases, we give them special names because those are the most common, the most used ones. The left Riemann sum is when we always choose the left endpoint as the height marking point. When we always choose the right endpoint, we say it's a right Riemann sum. We choose the middle endpoint, the midpoint. We call it a midpoint Riemann sum or mid Riemann sum. We did this in the example before for the velocity area under the velocity curve for the midpoint Riemann sum. We're now going to do a right and left Riemann sum. Riemann, just for those who didn't know, German mathematician, lived in the 19th century, 1800s. Interesting facts about him: very, very devout Christian, advised by Gauss, one of the most famous and most prolific mathematicians of all time, in Göttingen, and died very young of tuberculosis, I think. He created the foundation, the theoretical foundations of this calculation that we're doing here of finding the area under a curve. Ideas like this existed before, but he was the first one to formalize them using those names and definitions. So congrats to him. He also created this area called Riemannian geometry, which serves as theoretical foundation for relativity theory and many other fields. All right, so let's go into calculating our first left and right Riemann sums. They will be, you see here, we're using a graph of the function f of x equals 3 root x. So maybe I will follow it along that way. And we're going from 4 to 16. So that will be my 4. And that will be my 16. Trying to be a little bit to scale, but not necessarily. How the graph works of the square root function. It's kind of like this, right? And I'm trying to find, if I start with on item A, using a left Riemann sum with 6 subintervals, I have to first divide the interval 4 to 16 into 6 parts. So my delta x, so that means n equal to 6. Maybe I should do that in blue, so we'll do n equals 6, and therefore delta x is 16 minus 4 over 6, so that is 12 over 6, so that is a 2. So that means each subinterval, each rectangle will have base 2, okay? So if you want to make it look a little better, I will divide this in 6 parts, and we can label each of them accordingly. Every 2 we go 6, 8, 10, 12, 14, and then 16. All matches up perfectly fine. Because we're doing a left Riemann sum on A, we're going with the height of each rectangle determined by f of the left endpoint. So f of 4, right? So the first one will be f of 4 times 2. That's the area of the first rectangle, right? The height is f of 4. And then plus f of 6 times 2. They are all base 2. Right? This is f of 6. And then f of 8 for the next one, f of 10 for the next one, f of 12 for the next one is the height, f of 14 for the next one, and 16 doesn't show up. So f of 8 times 2 plus f of 10 times 2 plus f of 12 times 2 plus f of 14 times 2. One way to simplify this is to maybe pull out the 2, right, and just do f of 4 plus f of 6, up to f of 14. Note that, a cool observation about this, the 4 shows up, and every other grid point shows up except for the 16. The 16 does not show up on the left endpoint Riemann sum. And now all that it's left for us to do is to perform this calculation. It's 2 times 3 root 4 plus 3 root 6 plus 3 root 8, and so on, up to 3 root 14. It's not going to look necessarily pretty. You can simplify that if you want. Use a calculator, depending on what the problem's asking you. But that is our approximation. One observation. If you add the areas of all of these red rectangles, they're all under the curve, right? So we're always missing some parts here. So that is definitely an under approximation. So we're approximating this, but we're not quite there yet. We know the actual area under the blue curve is bigger than this number that we found. Okay? So this approximation for A underestimates the actual area, and then the approximation for B, I'll delete this. Maybe I shouldn't delete it. I'll just move it. Will be an over approximation because on B we will use a right Riemann sum, so it's the exact same grid points. So 4 to 16, but now we are using right endpoints. So we're doing same numbers, 6, 8, 10, 12, 14, and 16. But now we're doing right endpoints. So when I go here, I'm using f of 6 as the height. So I'm going this way. So now each rectangle will be higher. Right? We'll have bigger area than the area it's trying to approximate. So this will be an overestimate. But again, they all have base 2, right? They all have base 2. And the Riemann sum using right endpoints in this case is, what will it be, right? It will be, split this up so we can do the math. It will be, in purple, first rectangle base times height. Maybe I should do the height first for uniformity. F of 6 times 2. So this first rectangle has area, has height f of 6. The second one has height f of 8, and so on. F of 10 times 2 plus f of 12 times 2 plus f of 14 times 2 plus f of 16 times 2. I like sometimes to count to see that I do have the 6 intervals. 1, 2, 3, 4, 5, 6. I do have them. Note again that now I started at 6, so the 4 doesn't show up, but all the other points do show up on this calculation. So all I need to do is repeat the idea and calculate 3 root 6 plus 3 root 8 and so on up to 3 root 60. So the left one is an underestimate, the right one is an overestimate. That's not always true that the right one is an overestimate and the left one is an underestimate. It depends on whether the function value is positive or negative. So for example, if you imagine that the blue graph is under the x-axis, then these roles switch. The left one overestimates and the right one underestimates. Actually, not under or over, but increasing or decreasing, right? If the blue graph is decreasing, so maybe a graph like this, right? Then the left one is an overestimate and the right one is an underestimate. That's what determines whether each one does which. This third one is another midpoint, but I'm not going to do that one because we've already done a velocity example before with a midpoint Riemann sum. Okay.